Okay, good afternoon. I'm Arunima Banerjee from Department of Physics, ISSAA Tirupati. I don't think anyone is from ISSAA Tirupati today here among the audience. No. Okay. So I'll be talking about machine learning in astronomy and astrophysics in the next 1 hour or so. And then we can take up questions in the 15 minutes. But you are most welcome to stop me if something is unclear to you. I'll take it up if possible at that time. Okay. Please stop me, otherwise it gets difficult. We won't be able to follow what I say later. So feel free to stop me. We have a lot of time. Right. So machine learning in astronomy and astrophysics is a vast topic. Okay, I cannot do justice to it in a 1 hour talk. Okay. Pointer. Now it will work. Okay, so this is the plan of my talk. So essentially, I will tell you, I'll give you a broad overview of, starting from what is artificial intelligence and machine learning. So what most of us are acquainted with, I will presume, is programming. So what is the difference in philosophy? Or what is, how in principle programming is different from machine learning? We'll explore a bit of that in this overview, and then I'll give you a broad brush stroke picture of what are the different categories of machine learning, what are the different categories of machine learning existing. And as it will be a broad brush stroke view, I won't be telling you about, the most up-to-date. I mean, it's not an outdated thing which I'm going to tell you, but I'll skip a few things which have come up very recently. That is not required for you at this stage. Now, plus, first you get acquainted with what are the, essentials. What is the broad area, what broad classifications and so on. Which are the things which are already in use and well tested. See, things which are already in use are very well tested, right? As you know, we often don't go for the latest versions of Ubuntu, but because there might be a lot of bugs and all. So anyways, I'll give you an overall idea. So machine learning is broadly divided into unsupervised machine learning and supervised machine learning. We'll see what these are. And there are various types of unsupervised machine learning. Out of those, and to implement those various types of unsupervised machine learning, there are various computer algorithms. Okay? And I will be talking about one such case, which is one such algorithm, which is the principal component analysis, or PCA, which some of you may or may not have heard about. And by case study 1, I'll tell you about a project which we have worked on using this algorithm, this machine learning technique. Okay, so that comes under the unsupervised machine learning. Okay, just one algorithm I'll pick up and zoom in and tell you how it can be applied. And one reason I've picked it up because I have used it, no doubt about that. But the other reason is it is widely used. It has been widely used. And it's quite versatile. You will see when we go and talk about it, you will see there are various problems where we can use this algorithm. Then we will come to the machine learning, supervised machine learning techniques. And again, there are various types of supervised ML and various algorithms to implement those different types of supervised machine learning algorithms. We will again pick up this one, the convolutional neural networks, or CNN, and talk about two-case studies. Okay. Again, because I have actually worked with this, and also because they are quite versatile, these CNNs. you can use them for a lot of applications in astronomy. Finally, I will summarize and end with the references. Okay. So what is artificial intelligence and machine learning? See, we are acquainted with computers since late 90s, I would say. Most of us had computers at our homes, maybe from the 2000 or so. But artificial intelligence is, of course, usage of computer machines that mimic cognitive functions. Okay? So you are actually, it is almost like robotics. Robotics is a specialized branch, okay? But it is to make the machines behave like humans as far as cognitive functions are concerned. So what are the cognitive functions? What do we mean by cognitive functions? These are the multiple mental abilities like learning, thinking, reasoning, remembering, problem solving, decision making, and attention. Okay. So with our programming background, are most of you familiar with programming? Okay. So you can write and make out, right? If I ask you to write a program to mimic this so-called cognitive functioning, you cannot, right? One cannot program it without programming background, right? If I ask you to write a program that will do an AP series, GP series, you can, most of you can, right? Or at least you can, you know it can be done. But mimicking cognitive functions is a different ballgame altogether. Okay. So this is what artificial intelligence or AI is all about. There is a altogether different approach to developing models based on AI. It is not simple programming logic. No. Okay. Now, what is machine learning? So, machine learning or ML comes under AI. AI is mimicking cognitive functions by machines. Machine learning is computer algorithms that improve through experience, there is a typo, unlike a computer program. See, a computer program, there is no scope for improvement, right? Once you write it. That's the final version. You can, of course, go and change it. Okay. So a computer program doesn't iterate itself and improve, right? So that is the basic difference between machine learning and a machine learning algorithm and a computer program. Okay. It learns through experience. So this experience is something you should keep in mind whenever you talk about ML. Any ML algorithm learns through experience. Once it has learned. Okay, then you can use it. Every time you are using it, will not require you. I mean, every time you are using the trained ML or the final ML, that is then it is not learning from experience. Also, nowadays there is something called reinforcement learning. Every time you use it, it learns. Like we, learn from our mistakes in the exam, right? But let us, as I said, ignore, those fine things which have come up recently. So as you are writing up the code, it actually, I should not writing up the code. It actually gets finalized by experience. We will see, what I'm talking about. So now let us come to machine learning, the unsupervised machine learning techniques. Broadly, they can be of two types: clustering and association. Okay, so when I walked into the class today and slowly most of you came in, I could already see there were two clusters in the room. These girls were sitting on this side and the guys were sitting. Already there was a clustering, right? Anyways, so if I give you a mixed bag of, say, there is a cage, or I give you a mixed bag of images of dogs and cats. Okay, or maybe I don't give you. I give it to a 2-year-old kid. And suppose, we can communicate with the kid, and I ask the kid to separate out the two types of images. Do you think the kid will be able to do it? Yes, right? No. Yeah, maybe dog and cat would be little difficult for the kid. Maybe a little bit grown up, maybe 5-year-old kid. They can suppose they had just assumed they didn't know what is a, I mean they didn't know dog or they had by that time till that time they didn't see a dog and a cat. But there are differences, right? Okay. But suppose I give you two very exotic, the images of two very exotic animals, right, which you haven't seen until now. The images, there are, I mean, the images of the animals, suppose animal A and an animal B, they are not, the images of animal A are not exactly same. Like here, the dogs are, the images are different, right? They are not the exactly copy of each other. But even then, I mean, with cognitive functions, we can separate out, right? How are you doing it? I mean, something is happening in our brain, right? So we are actually doing a clustering operation. We are clustering things which are similar, more similar to each other compared to the two groups. Okay. So that is a clustering technique which comes under the unsupervised learning. Grouping things together which have a similar attribute. Yeah, I mean from the cat and dog, you can, I mean the face is different, right? Although you know, two eyes, nose, everything, four legs, etc. But there are differences which you can make out. Okay, how you are actually making out will be more clear when we come to the framing part. Features. Okay, the features are different, right? The cat has a roundish face, the dog has a. So anyway, that is how the machine learns. We'll come to that. Now, what is the other type of unsupervised learning? Association. Okay, and this association, when I was preparing this talk yesterday, yeah, I saw that you know this is often used in the supermarkets. So they give you their bills, like credits all entered in the computer. They want to see, suppose customer, these are the four customers. The first customer has taken milk, bread, butter. The next one, milk, cereal, bread, butter, milk, bread, butter, sugar and eggs. Okay. So there is, it looks like the customers who go for milk mostly go for bread and butter, right? Why are they detecting this friends? That's just an aside. You know, in the supermarkets, how do they decide which articles to place after which articles? Of course, the food items would be somewhere. But among the food items, how do they decide? This is how they decide. They actually run an unsupervised association algorithm or machine learning algorithm to find out these clusters so that it is easy for the customers to buy these articles. See, if you keep milk here and butter somewhere here, it's likely that the customer will not be able to press that. They will go out and get it somewhere from nearby their home. So if you place these articles close together, it's easier for them and hence they will be tempted to buy. Right? Also, sometimes they send you offers. Right. So I was reading some, which book I forgot. There is anyway, I'll tell you that later. So suppose somebody, yeah, somebody, I will tell you the story where I read that. There was a would-be mother and she was buying all this, you know, oversized clothes and all. So from there, the supermarket or the store could make out that that lady was going to have a baby. And it seems they started sending by email all this, you know, discounts for them, especially for them, for the articles of the baby food after 6-7 months. It actually happened, and the person got actually enraged. You know, these were early days, not this era of data science also, 30, 40 years back. And they, in US, you know, this quite often. They said it was an intrusion into their privacy. How do they know that we are going to have a baby? Why did they track this data? I mean, they did it in a good spirit, right? Of course, they will gain and it's business for them. But this is how it all happens. They track, you know, which things go together. Nobody is going there and sitting, you know, this so and so is buying all these kinds of dresses. That means I mean, next they will buy these things. No, it's a huge database, right? And everything is done, it's automated by the machines. So this is where this association ML, unsupervised ML, association algorithms come in. Okay. So I will be talking about the principal component analysis algorithms. So these are the types of models, but to implement these models, we need algorithms, right? So PCA comes under association. For clustering, there are various things like k-means, etc., which we are not going to talk about. Right. Oh. So we are talking about unsupervised machine learning techniques. Clustering, I made a mistake. This should be association algorithms. Okay, it is not clustering. I will change it. Okay, so read it. Pretend that this is association algorithm. And we have the principal component analysis over here. It is a computer algorithm. In short, it is called PCA. So what does it do? It actually, suppose I have three parameters, x1, x2, x3. Okay, some parameters, and it is not a three-dimensional parameter set, it is an n-tuple, suppose n-dimensional space. It's a huge data set. So in general, I want to reduce the dimensionality of this higher dimensional space. Sometimes it happens, right? For example, if you remember your simple harmonic oscillator, phase space, X and P. Okay. Although X and P are allowed to take any value in the XP space, right? Positive, negative values. But you know, if the energy is conserved, it will be on the ellipse, right? So from 2 dimension, I have made it 1 dimension, right? So dimensionality has reduced. So if I tell you what is E, the total energy, then only one variable of X and P is independent. The other is automatically determined from that equation, right? X square by A square plus P square by whatever, you know that. So it is kind of dimensionality reduction that is in the language of maths or computer science. In physics, we can say it is not quite, decreasing the degrees of freedom, but anyway, it is, we just have one. Since E is conserved, I know if I tell you X, you can be able to tell me what is P. Here also, suppose these are the height, weight, BP, sugar level, all these things of individuals in a population. And medical survey is going on and they want to see which parameters are related to which diseases or which symptoms are. Suppose we didn't have any background knowledge of medical science. I just want to, looking at the trends, I want to make out. So what it does is, it finds out the directions in this space where the variation is maximum. Okay, variation in the data is maximum. See, already you can make out if these are my data points for a population of individuals. And suppose I am only talking about a three-dimensional space, 3 attributes, height, weight, and BP. Okay, blood pressure. You can already look at the data points and see there is kind of a dimensionality reduction, right? It is not scattered all over the three-dimensional grid. There is one particular patch, and it looks like it is only in this patch that the data has the highest variation. See, in this direction, in PC2, whatever PC2 is, I will come to that. The variation is much lesser compared to this direction. There can be another direction also, right? So what PCA does is it finds out the 3 directions along which the variations are independent of each other. The variations are maximum and maximum, 1, 2, 3, maximum 1, maximum 2, maximum 3. There can be 3 directions only because my parametered space has 3 dimensions, and I find out those directions along which the variations are independent of each other, but at the same time the variations can be maximized. And how do they do that mathematically, since you are all
always possible?
Sorry?
For each data set, is it always possible to find two such principal directions?
In such principles, yes. But I'll come to that. The contribution might be very different. PC1 is the one with the highest variation, PC2 with a smaller variation, and so on.
And they will remain independent.
They will remain independent. Yeah, statistically. So how we do that? We know what is covariance in statistics. Most of you may know what is covariance. We obtain the covariance matrix of all these variables for all these population values, and we choose those directions, those coordinate axes, okay, which will diagonalize the covariant matrix. Okay, this is how this is mathematically implemented. What I said just now, I want to find out the eigenvectors of the covariant matrix. That is effectively finding out the directions along which your data has maximum variations. Okay, maximum 1, maximum 2, maximum 3. If it is 3 dimension, your matrix will be, you can give you only you will have only 3 eigenvectors. Okay, 2 dimension, 2 eigenvectors. But depending on the eigenvalues, you will know which one has which axis, which eigenvector shows the highest variation. That is called the principal component 1. Second highest is called principal component 2 because it has the second highest eigenvector, eigenvalue. It can have degenerate values also, but usually that doesn't happen. So that is just to tell you or give you a flavor as to how mathematically it is done. Okay. See, this is the, now I have forgotten about my initial axis and I have my PC1 and PC2. So in general, the usefulness of principal component analysis is it helps to reduce the dimensionality of the problem. From 3 dimensions, I have actually come down to 2 dimensions. Because only in these 2 dimensions, the data varies. The other is redundant, right? Suppose you have x and y values, but all your x values are constant. Then why to take the y value at all, right? I mean, we'll just reduce the problem to a 1-dimensional problem. Similarly here, by looking at these trends and doing this exercise, we can reduce the dimensionality of the problem. Okay. Now let us see how we have applied this to a research problem.
In that, how do we interpret the PC1 and PC2? The x1 is 5 to PC1.
Very good. There is no interpretation. It is just a linear combination of these 3 axes. Like eigenvector, right? You have done this moment of inertia ellipsoid, suppose. You know what are the principal axes of the ellipsoids, right? And those are the eigenvectors of the ellipsoids. Because if you use those principal axes as the eigenvectors or the coordinate axis, you will not have cross terms, right? But physically, in such a case, there is some physical interpretation. Those are the principal axes, But here there won't be any physical interpretation. As I said, the main idea is dimensionality reduction. For example, in your central force problems, because angular momentum is conserved, you convert the 2-dimensional r theta problem to a problem in the r dimension only with that Coulomb potential, Coulomb variator. It has to come, that is the contribution. Right? Similarly, I am just doing away with 3 dimensions by noting this trend. It doesn't have any physical implication. Okay. Right. So, this is the problem we studied, and I am interested in this very thin galaxies. These are disks.
For dimensional reduction, we need, there will be some scatter along each dimensional here as well.
Yeah, we can neglect. So, if PC1 and PC, we will consider only first those number of pieces which will explain 85 or 88. That is a matter of choice or taste.
Can send it. And 46, like, these are not, real random variables. They are some characteristics.
Height.
Yeah. Attributes.
That's a very good question. If those are attributes, I don't think directly using PC we can do that. I don't think PC directly. Yeah, but that's a very good question. These are also variables which can take a continuum of values. Okay. Now let's look at a problem, research problem. These are very thin galaxies. So these are disk galaxies, not the elliptical ones, but the orientation is edge on with respect to us. So if the symmetry axis is perpendicular to the, suppose this is the sky, symmetry axis is perpendicular to the plane of the sky, then the galaxy is called face on, the inclination is 0 degree. The perpendicular to the sky, the angle between the perpendicular to the sky and the symmetry axis of the galaxy, 0 degree. That is a face on orientation. What is edge on orientation? This is the perpendicular to the plane of the sky. This is the symmetry axis of the galaxy. The angle is 90 degree and that is an edge on orientation. So these are all disk galaxies and in almost edge on 90 degree orientation. That's why they look like almost a line. But we know the galaxies have some thickness, right? They are like a flattened cylinder, I would say. The height is not as much as big as a cylinder. They are flattened cylinders. So there are many edge-on galaxies. But what is the speciality of these galaxies? They are razor thin. Even Milky Way, to our vantage point, is a edge-on galaxy. There are other edge-on galaxies. Our nearest galaxy, Andromeda, is 75 degrees inclination. That's why it looks like ellipse. But these are almost like 88 degree, 90 degree and so on. But even then we don't expect a thickness of this much. How do you measure the thickness? From the major to minor axis ratio. Okay, A is the major axis and B is the minor axis. If it is for normal galaxies, it is around 10. Okay, in optical band. For this kind of galaxies, it goes till 20. 15, easily till 15 to 20. So they are very thin galaxies. Now, what is the problem? The problem is, firstly, they are razor thin and bulgeless, which means, see, in the plane, these galaxies are rotation supported. Okay, that means inward gravitational collapse is prevented by the centrifugal force or the angular momentum. But perpendicular to the disk, they are pressure supported, like your atmospheric waves. So this means
slightly unrelated. Slightly unrelated question, but what I understand is that bulges are due to the dynamical friction, right?
No, not dynamical friction. Dynamical friction is a very different thing.
Yes, but the bulges are formed because.
No, I'm not talking. I'm just saying why these galaxies are thin, not the bulge part. Okay. So
this thing is preventing the formation of bulge.
That is a different issue. I'm not going into the bulge. I'm just saying why they are razor thin. So this is decided if they are in equilibrium. I mean, there are various reasons why we can assume the galaxies to be in dynamical equilibrium. So this is set by a balance between a gradient in the pressure in the vertical direction and the gradient of the net gravitational field in the downward direction. Now the gradient in the net gravitational field is almost the same, if not smaller for this. These are intermediate mass galaxies. They are asymptotic. Limit the total mass is about 100 kilometers per second. Our galaxies is 200 and dwarf galaxies is around 50 or lesser. Okay. So if at all, right? But what is the other factor? The gradient in pressure. Or what is pressure under isothermal assumptions for ideal gases you have studied, right? Rho sigma z square. right? So it looks like sigma z square, that is this vertical random velocity, is very small, because of which they have a very thin. If they were high, if you think of an SHN, simple, I mean, for small contributions, you can think that this the stars undergo oscillations about this z equal to 0 midplane. If these oscillations were large, which would be a proxy for the dispersion velocities, right? Oscillations, the velocity is large means amplitude would be large, right? Then we would have seen a puffed up disk. But what we have seen is small. That means the velocity dispersion mean is 0. Right? That means the velocity dispersion is very small. Now, if you have velocity dispersion small, there are various implications. See, on small scales, right? Your gravitational collapse is counterbalanced by pressure. On larger scales, it is counterbalanced by the angular momentum. So there are two factors which can counterbalance the gravitational collapse. Locally, it is the pressure, and globally, in a large radius, it is the angular momentum. So this means if your disk looks so thin, which implies your velocity is very small, that means it won't be able to withstand the gravitational pull, and hence the disk should have been, bent and buckled and collapsed. Why hasn't it happened? That is mystery number one. Mystery number two is margins are quite common in the local universe or at some era. I mean, galaxy mergers were quite common. How come they have, withstood all the flyby effects and so on and so forth and retained their resulting structures? If there were some flyby galaxy, there would be a tidal effect. They would have heated up the stars. They would have then oscillated much more irregularly about it, and we would have seen a puffed up structure. Why aren't we seeing that? So all these things are interesting. So we listed a few parameters which could be responsible for the super thin appearance of this disk. So one thing for sure is the gravitational potential of the dense dark matter halos. Possible, it is possible. These galaxies have very dense dark matter halos. Now, in big galaxies like the Milky Way, what happens due to this feedback? This classic cast 4 problem. The simulations, the dark matter only simulations predict that the density of the dark matter halo should be cuspy. That means almost infinite density at the r equal to 0, and then it falls off. So rho dm is our cusp. But what observations show that it is core, constant density for some region around r equal to 0, and so on. So we model the rotation curve, right? We don't model density. Density is something we put in. So it is possible that these galaxies have very dense dark matter halos, because of which, if you are sitting in a very dense, deep well, whatever flyby and whatever happens, it won't be affected, right? So possible that they have a dense, deeper, they are sitting in a deeper potential well because of this dark matter halos, different kinds of dark matter halos, because of which they have withstood any kind of contributions. Got my point, right? So this is like this. If you have a shallow potential well, and if you are sitting here, if there is a kick, you will fall, right? But if you are sitting in a deep potential, if there is a kick, you will go and get you fall back. Right? Same thing. That is one possibility. So the dark matter halos of this kind of galaxies were investigated from rotation curve or some other observational means. Let us not get into that. My authors including us. The other thing is specific angular momentum. So suppose I have two disks, and those two disks are made of some material. Suppose if I spin it, if I give a larger torque to one of them, they will flatten out more, right? Compared to the one which I give a smaller torque. Suppose they are made of some jelly-like material or something, which can, as a result of which they will spread out, right? So I can say if the disk has higher specific angular momentum, it has to be normalized by mass, right? If the angular momentum per unit mass, for whatever reasons, maybe they were exposed to larger torque values or whatever, if the specific angular momentum of these galaxies are higher compared to normal galaxies, they will be thin, right? Mass is the same. If they spread out over a larger area, that means the area of the cylinder is larger, the height has to be small because volume has to remain the same. Something like that, just to give you a toy idea. Got it? They will be thinner, right? That is another possibility. The other possibility is other galaxies, have been exposed to all these gravitational interactions. They are located maybe in more dense environments. Okay, maybe these galaxies are located in sparse environments. As a result, they have not been disturbed, and as a result, they have not popped up. That is also another possibility. Yeah, low vertical dispersion and stability. I mean, that is a byproduct of all this. You can have low velocity dispersion if you are in an isolated environment, or if you have a dense dark matter halo, deep potential city. So these are many factors which can contribute to the thinness of this special type of galaxies. Okay. So what we did, see, look at these parameters first. This is my A by B. This is which larger A by B means thinner galaxies. Principal axis, major to minor axis ratio. Then I have my specific angular momentum. Then I have my QRW. This is some stability parameter. You know that if the second derivative of the potential is less than 0, it is a maxima, greater than 0 is negative. That is a stability. Even if your system is in equilibrium, for example, the pendulum, even if it is in equilibrium, there is a question about stable equilibrium and unstable, right? This is why theta equal to 0 is a stable equilibrium, and theta equal to pi by 2, theta equal to pi is also an equilibrium, but this is an unstable. So stability also matters. Unstable. Suppose I have something like this, no, and my galaxy is sitting there. Little bit disturbance will make it unstable. Right? So that is the stability parameter. How to calculate it or not, let us not get into that. And that is another factor. Then you have this vertical to planar dispersion ratio. Dispersion in the vertical direction to the radial direction. If this ratio is small, that means your disk will be thinner. Right? And finally, I have this compactness parameter, which tells you how much of the mass of the dark matter halo is located in the inner region of the galaxy. How this particular parameter tells you or not, we don't have time. I mean, for you, suppose you know that, or I tell you, these are the 4 parameters which any of these may be crucially responsible for the super thin structure of the disk. Right? Either the concentration of the dark matter towards the disk, or the high specific angular momentum value, or higher dispersion in this direction, lower dispersion in this direction, vertical compared to the radial, or stability. Suppose I take this. This is like your height, weight, blood pressure, whatever. So I do a principal component analysis. That means I find out the directions. So I have my 5-dimensional space now. I obtain their covariance matrices and find out the eigenvectors of the covariance matrices. That will ideally always help in the reduction of the dimension. So here these are my PCs. PC1, PC2, PC3, PC4, PC5. But I have put a square over here, right? And with what it means is more than 85% of the data is explained by these two directions. That means it's almost a two-dimensional data. Okay. So I can actually forget about the other directions.
How did we determine the prior distribution to get the covariance matrix?
Prior distribution is not required. Covariance is this, right? Prior distribution is not required. Covariance is something else. This is xi minus. Got it, right? Covariance may be. This is a statistical. Sigma x, sigma y. This is my covariance x. Here I have 5 x's. I mean 5 x1, x2, up to x. Anyways, so what we find that it's effectively a two-dimensional data. That means if I add, if it is a two-dimensional data, it is similar to what I was telling. Suppose all the data are located in this direction. Suppose I had I start with a two-dimensional data and then I find after doing all this exercise, actually all my data are on the x-axis. So I can effectively work with the x-axis, right? Now what I do, so that is a different thing. Here I got two dimensions. So all my data are located in this plane given by PC1 and PC2. Now what is PC1 and PC2? They are nothing but linear combinations of all these 5 attributes over here, right? So PC1 is like summation over AI like this. AX, X cap, BX, AY, Y cap, like this, up to 5. Here also PC2 is also like this. If I add this, I can add this, right? I will get the direction of the effective direction along which most of the data are located. Take that, right? Component by component I add. So what I am getting is a one-dimensional equation, an equation of, actually my data is located in one dimension, or that is geometrical interpretation, or I have a single equation connecting all these variables. Okay. And I see that the major contribution, after I do this summation, I get this effective PC, and this effective PC is constituted of a linear combination of specific angular momentum, stability, this ratio, compactness, along with A by B. So what we notice interestingly is A by B has the largest contribution, and with that contribution, the equivalent contribution comes from the compactness parameter. So what does it mean? A by B is strongly regulated by the compactness parameter. There are other contributions, but they are not as high as the compactness parameter. So essentially what we do, let me just release this and tell you. From PC1, PC2 is giving me 88% of the variation. Now I add PC1 and PC2. I get the effective PC, the direction along which most of the variation. It may not be very thin, but there might be a little scatter. And I get that this is my A by B contribution. And then I have my specific angular momentum. Then I have my stability parameter. Then I have my this ratio. And then I have my compactness. Then what I do, I normalize with this coefficient, A by B coefficient. See, this technique will only work in the case when the A by B coefficient is one of the largest coefficients. Suppose it drops out from the picture, then this technique I cannot use to understand this problem. There is always this caveat. I mean, statistics, this is how statistics works, right? Then, but luckily for us, it didn't happen. So this coefficient is 1, and all other coefficients were either much lesser than 1 or equivalent to 1. Okay. So we found that this compactness parameter had a contribution which was equivalent close to 1. All other factors were much lesser, which means A by B almost varies linearly with this. Other parameters have dropped out of the picture, which effectively tells us that as you increase compactness, A by B will also increase, which tells us among all these parameters, A by B is primarily governed by the compactness parameter, right? Not so much by the Q stability. Okay, but again, the caveat is it so turned out that we could use this argument here because these coefficients came out to be much smaller than these two coefficients. Had it not been the case, if these coefficients were much larger and this was 0, it would have been inconclusive. You know, right? In statistics, when you use this Kolmogorov's one-off kind of test, it is meaningful only if the p-value is much less than 0.02. I mean, for senior audience, I'm saying this. So it is not expected whenever you apply any statistical test also. This is a machine learning test anyway. You will get conclusive yes or no answer. No. Sometimes the test can give you inconclusive results. That holds good in machine learning also. So luckily, we were lucky. It didn't give us inconclusive results. Yes. Yes.
How is it different from like direct correlation statistics without this correlation?
How will you? This is a multi-dimensional space. How will you find out? There will be pairwise correlation. We are finding out the covariant matrix anyway. It will be difficult to draw the conclusion, right? See, we are effectively reducing the dimension. PCA's main intention is first to get rid of the variables which are not contributing to the picture. And then finally we are getting a linear relation by some assumptions like implementing some choice, and then from there it is easy. Otherwise, so many directions. No?
So main advantage is for like high dimension.
It's high dimension. Main first line for PCA is dimensional reduction. Okay. So this was one case study for unsupervised machine learning. Now let us move to supervised machine learning. So what is the difference between supervised and unsupervised? In unsupervised case, there is no label to the data attached. Like as I said, those pictures, cats and dogs, it was not written cat, this is dog, you have to learn. Like, the children have taught. There are picture books, this is apple, this is how apple. That is a supervised, not machine learning, but okay. That is a supervised training, right? But if you just give the alphabets to the kids or photos of apples and oranges to the kids, the kid might, be able to sort it out. The kid might not know that it is apple or that is orange, but they will be able to sort it out. That is unsupervised, without any label on the photos. But supervised means there is a label. Wrong or right will be told. Okay. So there are various methods. Okay. But we will again discuss about this convolutional neural networks, which comes under the artificial neural networks. These are the computing systems inspired by the biological neural network. Okay. I also want to make a comment over here. These are much less compute intensive. Okay. This regression, support vector machine, this can be done using your laptop. This cannot be done. This is compute intensive. And these are mostly used for classification of images. It can be a binary classification or classifications with apple, orange, mango, like this, discrete classes, or it can be a regression. It can give you a continuum of numbers. So I started working in this area after coming to IUCAA. My office mate Shilu Abraham used to work in this area, and she was classifying barred and unbarred galaxies. Okay. So either yes or no, barred or unbarred. But there is something called the barred length. So you can also train the convolutional neural network not only to say whether the galaxy is barred or unbarred, but what is the barred length. That will be a regression type of problem, not only a classification. Classification will only tell you bar, unbarred, spiral, this, that. Regression will give you a number, and that number is always a continuum. Anyway, so let us look at this convolutional neural networks. So this is a supervised machine learning technique. So I am teaching the machine to recognize the picture of who is this Donald Trump. Right? Yeah, Donald. Oh. Okay. So they have not given Goofy or Tweety. I also don't know them. But see what they do. Convolutional neural network. What is convolution? Some of you may have done it in your Fourier series or Fourier transform. You know, convolution. So you have a kernel, right? Kernel is like a stencil, right? So what it does is, these features are like kernels. There are various layers of kernels. Okay. It just pokes there and sees if there are edges, if there is a round means okay, there is, I'm just trying to give you a feel of it. If a round is present means okay, there is a circle, then it might be the face of it, then it will start looking for two other elliptical things, then nose. Okay, so these are the equivalent of the mathematical kernels you have in your convolution, right? So these features are implemented using kernels. Features are nothing. Firstly, in the first layer, they will try to detect if what are the edges of the pictures. Then they would try to, in the next layer, find out if there are arcs. Then they would go for finer and finer pictures. Right. After detecting all those, they will, so they are. This is a two-dimensional image, right? This is a matrix. Okay. And this is how the model is trained. So I have the answer with me. Okay. And I want the machine to learn that whenever this picture is given, the output should be Donald. Okay. Or suppose we don't, for a complicated model, I say whether the output is Donald or not. That's all. Okay. How does it do? It doesn't know actually. Okay. So what happens here is there are some matrices. Okay. And the entries of the matrices are not known to us. We start with some trial values. What convolution does is element by element multiplication of so my input image is a matrix, right? Pixel by pixel, 273, 273, whatever. Okay. Now let us take a very basic case. I have a 4 by 4 pixel. This is my input image. This is my input layer. I input the image. Then I have my convolutional layer. Okay. The convolution layers, there can be multiple convolution layers. 3, 4, 5. So each convolution layer is again a matrix. The dimensions have to be the same. Those can be adjusted. Depending on what is the dimension of your image, you can adjust those internal parameters. And see, these codes are nowadays available. So you can adjust those parameters, how many should be the dimension of your convolutional kernel that can be adjusted. So they do element by element multiplication. Okay. Element by element multiplication, what is it called? Outer product, right? And this is what? The outer output. So this is like A1, A2, A3, A4, A5, A6, and suppose B1, B2, B3, B4, B5, B6. Okay. So here after convolution I will get A1, B1, A2, B2, A3, B3, A4, B4, A5, B5, B6, B6, and so on. So this is my kernel, which is the mathematical implementation of the feature. Now what can be feature? Feature can be straight lines to begin with, then circles, all geometrical figures, slowly eyes, you are trying to any shape. So suppose my feature is this vertical line. Do you think this is a good representation of vertical line? Sorry, this. Okay. So that means only suppose this is this kind of a line. I want to detect if my input image has a line like this. Then only these pixels should have increased. Okay. Other pixels should be 0. The value of the pixel should be 0. So the algebraic representation of the geometric shape a line is 1, 1, 1. Now I don't know what is A1, A2, A3. These are my, this should come from my input images. They have some grayscale values. Okay. But in order to find out whether a line is present or not, I have to actually start working on these values. So the idea is the final image, this face, okay? It is a superposition of many such features. Maybe straight lines, squares, circles, this, that. I don't know what is the number, it's humongous. Maybe lakhs or crores of those features. And how have they created this repository of features? By all these years of training the various sorts of training, right? These convolutional neural networks have been trained for ages now. So they have a huge repository. For each shape, there is a matrix, okay? And the final image can be looked upon as a superposition of all these features, okay? Starting from the very gross features to finer and finer features. So actually, these are the trial values. Okay, I have to by trial and error, by iterations. That is what is meant by training the model. I have to fix these values such that I get the right answer. These values by trial and error, this is not a single set of values. The final set of values will be various matrices corresponding to each feature and each photo or image you have, each of the photos, right? So by going back and forth, like you have a set of data points and you have to fix a straight line, and ax plus b is the value of the function of the straight line. Okay? You start with some trial a by b. First trial gives you a line which is quite off. Okay? Then accordingly you change the slope. Then something this way, again you change. So by trial and error, you keep on attaining the right values of a and b. Very similar thing happens over here. You start off with a trial matrix corresponding to each feature. Okay, and see, after that you have a flattening. Okay, flattening. Okay. Finally, you superimpose all these matrices and values, but before that there is something called pooling. I pick up, after this convolution, I pick up only the value of the convolved matrix which has the highest entry. Okay, so that is what is known as pooling. Finally, I flatten out my matrix. That means I have a two-dimensional array coming from the convolution of each kernel or feature with my original thing, image, and correspondingly there would be a matrix. I flatten it. Instead of giving it in this two-dimensional form, I give it in a linear form. So this is the first row. Then I give the second row. Then I give the third row, and so on and so forth. And if you remember, I have pooled them. I don't give all the values. I just give the highest value for each case. So the dimension is reduced a lot. Just I try to get a flavor of the whole. It's quite complicated. And then I try to match it with my output, whether it should be a donut or not. So I should have images of a donut and I should have other images which are not donut, maybe a blank image. Okay. So the features which should correspond to donut should be present in the image which you are passing. It has to be classified as a donut, and it should have the, I mean, it cannot be 100 features only. It will be, there will be a probability. 90% of the features are present. That means you can say it is a donut. Less than 50%, not at all donut. Okay. And again, this whether you will go for 90 or you will go for 80, it is up to you. Okay. Usually in machine learning, your model is good enough if it is above 85 or 90. So if it is, we can say, okay, if it is less than 85% of the features are present, means you have not chosen in the training phase. Okay, you have not chosen the A1 values correctly. Go back. You go do back propagation. From the back, you start correcting. Again, you go back. Again, you see a mismatch. So this way, you have to go on iterating for about 60 to 100 epochs. These are the epochs, means the trials. Okay, and then after all these iterations, like your A and B values are fixed, the corresponding matrices for each of these features are also fixed. And this, keep in mind, you are not giving identical photos of donut. There can be various other photos. See, if you give me different photos of you, I can recognize that it's you only, right? How does my brain do that? Because I know these are the features. It doesn't have to be exactly the same. So that is what the machine should be capable of doing. So when you are training the machine, you should give different types of photos of donuts, which you and me will recognize, but the machine at that point doesn't know. So every time you give a photo of donut, the output tells it is a donut. Then the machine says, okay, only these features are not essential. There can be a mixture of these. Sometimes this can be higher, sometimes those features can be higher. Okay, then it's, so in some photos, suppose the donut has a hat. The machine might get confused, right? Usually we ignore those kind of. Suppose I am training a model to identify galaxies. Some galaxy has something, suppose more features which are not essential for my classification. Suppose a bulge. I will remove those from my training set because unnecessarily my machine gets confused, right? The machine doesn't know what to look for when I say it is a galaxy. Bulge is not essential. So if you give Donald's photo with hats and all, it will take more time. It will give on, go back and forth, and then it will know, okay, every time I see this kind of thing and the eyes like this is Donald. Hat or this thing is not essential. So it is through experience, right? It is learning. Because every time it is going, the probability is below 0.5, it is getting a tap on its head. Wrong, go back, again it is going back. Again it is changing each of these matrices. Okay? And finally it knows, okay, now I can identify, I know Mainly this kind of a beak, this kind of eyes and the face like this, these are the features of donor. It learns on its own. Because the teacher, there is a validation step, right, at the end of each epoch. It is like a class test. Every time it fails in the class test, it knows it has to correct itself. Then slowly it learns and comes back. But it's it's amazing that it is able to learn a machine. And we are seeing it everywhere, right? Nowadays, image recognition and all. Okay. So this is how it gets trained. These are the feature maps. This is the fully connected layer. After convolution, we have flattened it, reduced the dimensionality. Then we have done a one-to-one fully connected layer. That means for each case, whether it is a Donald, this sort of combination will say it is Donald. This sort of combination will say this is Goofy. Now these connections are actually weightages. See, suppose, how do I say? Suppose I have 4 features for similarity. Suppose in case of Donald, these are the main feature. In case of Goofy, these are the main features. And in case of what is that? Goofy. These are the main features. Right? So the connection with Donald and this will have 0 weightage, right? With Donald. This is the network picture. These are 1, 1. For this guy, this is Donald, right? Yes. And for this Goofy, the connection would be what? Only this and this. This one would be 0. Right? And for the other one, last one quickly, this one would be 0 and this would be 1. So if you have this sort of, now see, this 1 and 0 are extreme cases. It can be 0.75, 0.4. It is always a threshold. So if you get this sort of combination, I know this is going to be Donald. So this is how it decides. So this is how the model is trained. After the model is trained, you test it on a sample of data points which have not been used for training the model. A new set of images of Donald. And then you see if it is performing well or not. That is the final exam. Okay. So just, yeah, these are all taken from the internet. You can look up. This is the kernel step. This is the max pooling step. Just see, this is the input image. I don't know whether you can see it or not. This is the no. Huh? Yes.
What if the features themselves have some intersection? A line and a box, then a thick line will be detected as a box, and then it will have an issue because a lot of pixels might represent a line. And how will it differentiate?
It is just zooming in. Fine. In first step, they look at the edges. Then in the next step, they look at finer features. Then within those features there is something. So slowly it is going to smaller and smaller scales. Okay.
If we give features of line, if we search for features of line and box, should we set like the number of pixels within the sizes? Should we give a limit for differentiating?
It is just looking at the superposition of all these cases. So it can look upon the box also, either as a box with 1 weightage and 0 line weightage, or it will look at as 4 lines with 1 weightage and 0 box weightage. Either of 2 is possible. It has one big box of all these kernels. It just keeps putting and checking whether the output is giving is right or not. It is blindfolded. It only knows it is right or not. Okay. Okay. If you can switch off the light cycle. Can we switch off the lights? See? Firstly, it has taken up the outlines. And then there is a step called activation. Oh, sorry. There is a step called activation. It will actually accentuate the values. See, the lower features are present. Okay. But it will accentuate the values of the outlines. That is called activation. and then pooling, it will only take up the brightest among all. See, only the brightest parts are being seen. As I was telling, in pooling, you just pick up the one which is the highest value. That's why you are seeing only the outlines. So anyway, this was for illustration. We can switch on the lights. Right, and these are when you are training. At the end of each trial or report, you are checking how is your accuracy changing. Is it going away from, is it increasing or going completely way off? Then you go back and change the pool of data, training data. You know, there can be very complicated, noisy images. Let go of that. Why to complicate life for the machine? On the go, you can check. See, it can take 2 weeks or several days to train a convolutional neural network. But you can see these figures in real time if you want to. So if you see that it is actually going way off, just go back like we do, right? We change the trial values every time in our model. Right. Now, these are the parameters which actually tell you whether after your training is done, you are happy, whether your model is a good one. Suppose you give me a model, she also gives me a model. Whether among these two, which one should I take? So these are the parameters which tell you precision, recall, and sometimes harmonic mean of precision and recall. So precision is a good measure to determine when the cost of false positive is high. Suppose spam email. What is false positive? You have an important email, it goes to your spam box. So you should use precision as an appropriate measure of the goodness of the model when you are developing a machine learning model which will, try to detect spam emails. On the other hand, recall. It has a high cost associated with a false negative, like fraudulent transaction, false negative. That means there is a fraudulent transaction and you don't detect. In that case, you should use the parameter called recall. They are very simple parameters, so I'm not saying those. So the upshot is to test the trained model, you have all these measures. So depending on my requirement, I will choose my measure, and then I will, out of the two companies who are supplying me the trained models, I will choose the one with the higher value of the testing parameter. These were the real-time ones. When you were actually developing the model for your customer, you were looking for it, how to go back and keep changing the trial values or the architecture values, parameters, the hyperparameters associated with the model. Okay, so we have very less time, 5 minutes. So we have used this convolutional neural networks to look at two very basic problems. Firstly, there are two different kinds of spiral galaxies. These are called the grand design galaxies. Grand design spirals, clean, S shape is seen. And these are the flocculent spiral galaxies, very fluffy like a cat. And their formation mechanisms, the suggested formation mechanisms are also very different. So we designed a trained a convolutional neural network to identify flocculent, and this is flocculent and grand design galaxies. And for a long time, people had not, classified. I mean, new surveys are coming up. SDSS has now DR17. Nobody tried to identify new grand designs and flocculent from them because there are new galaxies images in those surveys, right? So using a convolutional neural network, we could identify about 700 grand design and about 600 flocculent. Flocculent 500, grand designs 700. So these are the grand design ones, the clean ones. The flocculent ones are the fluffy ones. So these were not categorized as, grand design and flocculent in SDSS DR17. SDSS DR17 could press many new additional spiral galaxies, but nobody had categorized it. So in earlier days, people would sit down and look at and then categorize, right? But using this machine learning model, they could do it in a matter of seconds. and that to 500. I mean, this could have been a PhD plus postdoc maybe 30 years back. So just sit and identify, do Galfit, find out the Fourier components and so on. So this was one problem in which we used CNN. The other problem was something which we did earlier. See, when I was working on a problem of finding out the dynamical parameters of an interacting pair of galaxies. So what I wanted to find out was what was the inclination angle of inclination between two galaxies, this angle, okay, between their symmetry axis, and also the viewing angle, that is how are they oriented in the sky. So anyway, we know if they are oriented edge on in the sky, they would look more like a straight line. If they are oriented in the plane of the sky, would look more like a circle, and so on. So there was a data set for interacting galaxies, simulated interacting galaxies called Galmer horizon. They had many simulated galaxies. For example, I have shown you some of the images. So the inclination angle between them is 0, and the viewing angle is also. So theta in this convention is opposite. In the convention I was telling you, theta was 90 degrees for this line. For them, theta is 0 degree. Anyways, that's just a matter. Here, theta is 90 degree. That is their face on. In their convention, they are calling 90 degree. I is equal to 0 degree. That is, the symmetry axes are both aligned parallel to each other. And so on and so forth. Okay? So we use this kind of images to train our model, and actually our model could predict correctly the viewing angle and the inclination angle of interacting pair of galaxies from the SDSS. Again, we treated it as a classification problem. Ideally, it should have been a multidimensional regression problem because inclination and viewing angle are both continuous parameters, right? But when I say 45 degree, I give a window of 5 degree, 5 degree. 45 means it can vary between 40 to 50 degrees. Similarly for 15 degree. Okay. We did this because we didn't have a continuum of simulations with, simulated images with parameters continuously changing. We only had input values for this discrete cases. Okay. So anyway, the upshot is using CNN, like just as you yourself can say, looking at it, that this is 90 degree and that is 0 degree, and maybe this is 45 degree. It's quite apparent that you can also train the machines to do that task for use, which would be very relevant in the next generation telescope era, right? When you will have terabytes of data generated in 1 second, and you would need automated devices to do the first-hand analysis for you. Okay, so that's all. I'll just end with flashing the summary slide, and we can take a couple of questions. Thank you. Yes. This one?
So what is the 2 coordinates x
Okay, this is the actual. Firstly, this is the actual we know, and this is the predicted. This is just to show you how well the model has fared. We have created the model on the simulated images, and we are testing on the observed images. So it is quite difficult. I mean, we were not expecting that the model could predict so well. Okay. And this is the relative inclination between the two galaxies, and this is the orientation in the sky. Oh, yeah.
And then we are doing that coordination so we have to split it into RGB.
Yes. For everything RGB. So everything will be 3 times multiplied.
Every, like for example, red light will be at
Yes, 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 yes. Lot of computations. That's why it takes about 2 weeks. At least 2 weeks.
So each of the methods are worked on separately.
Then we sum it off, then we flatten, then we cool, then we flatten, and then we dense, and then we say this is the ultimate output. So, lot of degeneracies, right? Firstly, there can be lot of degeneracies. That is what we want to aim. Because firstly, you are a single image can be looked upon as she just said, square or 4 lines. There can be many such combinations which will give you to the same particular image. Now, it is not the particular image. There can be various images of the same person, and that would each of them would have degeneracies as far as the combination of, and that is what you are looking at. If 90% of the features are identified, you are happy. Yes. Any further questions? Acha. If not, do we have questions online from online audience?
No, Arunima.
Okay.
Not so far.
Okay then. Yeah. Okay. Yeah.
In
Yes.
this principal component,
Hmm.
I am new to baseline. But in this case, I usually am new to baseline.
No problem.
So I know about this that it learns based on I only know of back propagation.
Back propagation will be coming here.
Okay. In that case, how is basic learning? Because I can understand based on the stock that there is this mathematical algorithm that we have this covariance matrix and we figure out the eigenvector, eigenvectors and all that.
That's all. No back propagation there. In principal component analysis, no back propagation is required. Here it is required where you are doing parallel. There you are just diagonalizing the covariance matrix. So,
like, what is it they are called machine learning in there?
huh?
I mean, how is it called machine learning in there?
Yeah, that's a good question.
That is the learning.
There is no learning. True.
Okay.
Yeah. So in that sense, I should say the supervised machine learnings are true machine learnings, right? Unsupervised is, but it goes, principal component analysis is something which is a direct process. There is no trial and iterations involved. But in clustering and other, like k-means clustering, where you identify there are iterations are. Because every time you cluster, you see whether this is the best cluster or that is the best cluster. So PCA maybe it's little bit dicey. Okay, shall we end the session?
Thank you.
Which data set?
HDSS, PR70. That was for the populant brand design, and the simulations were Gallman Horizon. Those are simulations.
How big is the data? What is your training set?
What's the training set was about total for the spiral galaxy 300 images total. It was a very small number of just raw images. After that, we did augmentation, rotation, and all those things. But even with 300 images, we could see that people won't believe that it happened. It all depends on the quality of the unit and features at the variety of images, right? It's less noisy.
That's why that is good at it.
Costing.
Not this, it's colored.
If it is
Watch these ones. That is the other problem. There are two problems. One is the information result problem. The other is lucky or this. SDSS, those things are only grayscale because it has channels for color. Those are actually color maps. I showed it because I took a snapshot. Otherwise, there is channel.